All right, so I've prepared a presentation on our confirmation and a further analysis of Kepler planet 550b. Now, it's a bit of background. Kepler satellite was put into orbit on March 6th, 2009. It was put into a heliocentric orbit, meaning a trailing heliocentric orbit, meaning that it's not in Earth's orbit or Earth's atmosphere. And this provides it with greater stability and things such as this. And it also takes about a week longer to complete its cycle around the sun than the Earth does. Now, the intent of the Kepler mission was to look at a region in the sky and stare at a field of stars between the Cygnus and Lyra region you can see in the photo provided. And the intent was to try to collect a frequency of planet types in other solar systems and to specifically look for how frequent Earth-like planets are. Now, the satellite's been designed to be really stable, to get really smooth data. The fact that it's not in Earth's atmosphere allows it to, it has reduced sort of forces that'll cause variation in the data that we're collecting. Now, the method that Kepler uses is known as the transit method. Essentially, by staring at the light given off by a star, when something crosses in its path, the light will dip, and if we see this dip coming in a periodic fashion, we may surmise this to be a planet in orbit. This is a little video demonstrating that as a planet goes in front of a star, the graph you see there, a dip will occur in the data, and by searching through your data to try to find these dips occurring periodically, we can confirm a planet in transit. So the benefits of this is it can give us an idea of a planet's size, its orbital radius, as well as the atmospheric composition, which is excellent information in determining how frequent Earth-like planets are. The difficulty with this is the difficulty with this is that you can only detect planets that are directly in your plane of sight. If a planet is a little above the plane or below, you're not going to be seeing the light that it's blocking, so you won't even know that it's there. And so NASA provides data from Kepler's mission you can see this link provided. And our data is specifically through the 2009 and 2013 mission. It was repurposed and continued on. It's still running, but we'll run low on fuel for the K2 mission. But our focus was on the Kepler's 2009 to 2013 mission. Now, we chose to do Kepler 550b because there was only one planet in the system, and our objective was not just to confirm the planet's transit, but to search for a secondary planet that we're not seeing because it's not in the plane. If there was a secondary planet, the idea was that this would cause some changes in the planet we are detecting's transit, so searching through the changes in this transit might give us some idea to that. So we collected the data from the Mikulski Archive for Space Telescopes, and then we extrapolated this with a TopCrop program and then put it all into Excel to organize it. A bit of a reference to this Kepler 550, the star we're looking at, is it's about 0.8 the size or the mass of our own sun, about 0.8 its radius, and with a 5,300 Kelvin, whereas our star is roughly 6,000 Kelvin, so it's just a little bit smaller of a star than our own. And the planet we were observing was about 4.5 times the size of Earth. As the star was also a rotationally variable star, which means that surface features caused a lot of noise in the data, lots of variations in the light intensity just because of the star itself. So because of that, when these images I've provided here are of during a transit. The image on the left is our raw data showing that variable nature of our star was creating a lot of flux within the transits. So we smoothed it out to get a better look in transit for our next approach, which was we used a what-if function to look through the data and find these center of transits. You can see on the left and right, the conditions we were using were based on how deep these transits needed to be. And then the idea of the spot in green, the A6, is that the center would have to be lower than the points to the left and the points to the right. Each data point was taken within 30-minute intervals provided by Kepler. And using these conditions, we were able to get approximate, where every transit we thought was going to occur. But because the data points were only within 30-minute segments, we figured the actual transit would have occurred between these data sets. So we used a line-est function to get the, what the line-est function does is provides the coefficients to a polynomial, and we specifically were looking for a quadratic. For the parabola, we could fit within our transit and then use the vertex equation, negative b over 2a, to find what we were going to consider the center of our transit. As we were going about this, we were finding that you can see in the picture on the left, there's this top left, on the top data point, that it was sometimes due to the variation in our star, this would cause our points to, the vertex we were setting in there to be dragged a little more to the left than we were expecting it to be. And so this was compensated by a shift to the right or left if the case was such. And by doing this, we were able to get what we were considered the approximate center of our transits. By taking the difference of these transits and then averaging them all, we got to a value you can see in green, which, as compared to other reported values, we were within 2 seconds. So we felt like we had some pretty good merit on the approach we were taking. But so our secondary objective was to look closer at these transits to see if some variation within the transits might indicate a secondary planet we're not seeing. The difficulty we found with this was that there was gaps in the data due to the satellite needing to be worked on for various reasons, and that anytime we did see a trend, it started to how the gaps were blocking us from seeing that trend continue to represent a periodic nature. The graph I've presented right here in blue is the difference between the total average and a moving average. We experimented with multiple methods to look closer at these transits to try to find a periodic nature to it, but in orange you can see we tried to fit a sine graph to it, lurking for this periodic nature, but because of these 100-day gaps in our data sets, actually in this graph, to the left and to the right of this, there was gaps, and so the possible trend kept being we lose the trend right as the gaps would occur, and so we think that to verify this method or to show that a secondary planet was there, we would need a little bit more continuous data. So all in all, we were able to confirm that this planet had a transit time of about 8.6 days, but with regard to a secondary planet, it was suggestive through the data that there could be something there, but we weren't able to get a periodic nature due to the inconsistencies with the gaps in the data. And that's my presentation. Any questions?
So first, how do they determine the forms of planets? Because you were talking about frequencies of discovering planets.
Right. So the depth of the dip gives us a planet size kind of a thing. And then the orbital radius, there's another technique I didn't quite get too into, but the atmospheric composition is also through spectral analysis.
Okay. And then you fit a wave on the sine wave. Was that a Fourier transform?
I did attempt to do a Fourier transform, but it wasn't what I showed in this graph. That one was just a single sine wave. But when we did the Fourier transform, it was also, we weren't finding data that was...
But the actual, you fitted a curve to the actual. How was that performed?
Oh, so the line-est function, by using a set of xy points, it provided us with that. And then by using the vertex equation, we just put those coefficients in to get that point.
And one more question, sorry. Transit time, is that the period of the planet orbiting around the...
Yeah, like how
star?
often it came about, a full year kind of a cycle.
Awesome, thank you.
Yeah. Is there any more questions?
I was going to ask, are there any other techniques or ways that we can use to kind of determine whether or not there is a planet around stars other than observing their oscillatory dimness in a way?
Another method we did kind of look into was thinking about the transit duration, like how long the planet was actually physically in front of the star. And if there was another planet around there, it would either cause it to increase the transit time or decrease it depending on where that planet was. But that also, because of the 100-day gaps, we weren't able to conclusively demonstrate that how we had intended. Any more questions?